Today we're looking at finding discontinuities of a function and then determining if those discontinuities are removable or non-removable. Now, what are some things we've learned that discontinuities can be?
Asymptotes.
Asymptotes?
Holes.
Holes? Jumps. Okay? That's what we're talking about with discontinuities, and we'll run into all three of those when we're looking today. Alright? Now, when we are talking about whether or not those discontinuities are removable versus non-removable, there's something that has to happen for a discontinuity to be removable. And that is that the limit at the x value where it is removable must exist. Okay? So, is a discontinuity that is an asymptote removable or non-removable? Why? The limit doesn't exist there. Okay? What about at a jump? Removable or non-removable? Non-removable. Because the limit doesn't exist. What about at a hole? Yes. Why? The limit does exist. Okay? So a discontinuity is removable if the limit exists. It is non-removable if the limit does not exist. Alright? So, what we're going to do is we're going to be given a function. We have to find the discontinuity and then determine if it's removable or non-removable. So, let's look at 35 to get started. On page 79. What's an easy way to determine when a function is continuous or when a function is discontinuous? What's going on with the function if it's discontinuous? What did we just say? When is a function discontinuous? We talked about three things. No.
No, like a jump.
Jump,
Asymptote.
asymptote, or a hole. What's going on with asymptote and hole as far as the function value is concerned? There is no function value. The function value is undefined if we're dealing with a hole or an asymptote. But if I'm dealing with a jump, can the function be defined? Yes, it can be defined above and not defined below. Okay? So the first thing we want to do is we want to look for holes or asymptotes. And we can look for holes or asymptotes by looking for what? Zeros in the denominator. Okay? I want to look for zeros in the denominator. So, on this particular case, I have f of x equals 6 over x. So what's going to make the denominator 0? Obviously, x equals 0. So that means I am discontinuous at x equals 0. So that's the first part of the problem, is finding discontinuities. The second part of the problem is determining if it is a removable or non-removable. Of our three discontinuities, which one was removable? The hole was. Why? The limit existed. Okay? Now, when I find discontinuities, how can I tell if I'm dealing with a hole versus an asymptote? Does anybody remember that? And I will tell you that this one right here is an asymptote, so that is going to make it
Because it's over.
non-removable.
Because
Here's how you tell the difference between a hole and an asymptote. Okay, you look for what makes the denominator 0. If what makes the denominator 0 can cancel out with something in the numerator, you're dealing with a hole. If what makes the denominator 0 cannot cancel out with something in the numerator, you're dealing with an asymptote. So in this case, what made the denominator 0? When I plug 0 in for x. X does not cancel with anything in the numerator, therefore I'm dealing with an asymptote. Okay? But let's say I had something like x minus 3 over x times x minus 3. What would my discontinuities be there? There are two of them. Don't be big. 3 and 0. Okay? 3 would be a removable discontinuity because it can cancel. So if it can cancel, you're dealing with a hole. If it can't cancel, you're dealing with an asymptote. So in this particular problem, this produces a hole, but this produces an asymptote. So if it doesn't cancel, it's an asymptote. If it cancels, it's a hole. So in this case right here, x can't cancel with anything, so that means I'm dealing with an asymptote. And if I'm dealing with an asymptote, what type of discontinuity is it? Non-removable. Okay, if I'm dealing with an asymptote, it's a non-removable discontinuity. Okay, hopefully it'll start clearing up. The more we do, the more comfortable you should get with it. All right, let's look at 37. F of x equals x squared minus 9. Are there any discontinuities?
No.
Why not? Because I don't have a denominator. Discontinuities come from when my denominator is 0. I don't have a denominator, so that means there are no discontinuities. It is continuous everywhere. All right, let's look at 39. I have f of x equals 4 minus x squared.
With a 1 in the numerator.
With a 1 in the numerator. What should I do to this?
Set the denominator equal to 0.
Set the denominator equal to 0. I'd rather you do something else though, but that would get you the answer. But I'd rather you do something else.
Multiply by the conjugate.
No, I only do conjugates when I'm dealing with what?
Radicals.
Radicals. So what are you telling me
A factor.
to do? Okay, I want a factor. So if the denominator is not factored, go ahead and factor the denominator, please. So, once I get here, I should be able to tell what makes my denominator 0. What makes my denominator 0? 2 and negative 2. So I would say discontinuities.
Is there any way we can abbreviate that?
No.
Because I don't know how to spell it consistently.
Is that a 2 plus of x?
Yes. Okay, I have discontinuities at x equals 2 and negative 2. Are those discontinuities removable or non-removable? Why?
That's an asymptote.
Because I'm dealing with asymptotes. Since I'm dealing with an asymptotes, that means these are non-removable. So I've got 2 discontinuities, they're both non-removable. So if I were to graph 1 over 4 minus x squared, what is happening right here? There's only 2 options. My graph either has to go up or it's got to go down at those 2 spots. Okay, very good. On either side. All right, let's look at 43. No, 41, sorry. On 41, I have f of x equals 3x minus cosine of x. What do you guys think?
No. I don't think there's
All right, why do you not think there are any? Explain what you think.
well, no there's a denominator at all.
All right,
If you plug any number into cosine, you're gonna get another number.
okay.
Well, I don't know.
All right, he's on the right thought process. Since this has 2 parts, you can kind of take each one of these separately. Okay, there's no problems with 3x because what?
You can plug any. It's not that.
There's nothing in the denominator. Okay?
Oh.
And I'm also fine with cosine of x because what does the graph of cosine of x look like?
Like that.
It looks like the wave. And there are 2 things that are not part of the cosine wave. What are those 2 things that are not part of it? There are no
Asymptote.
holes and there are no asymptotes. So since there are no holes or asymptotes, that means that it's continuous. So this thing would always be continuous. There are no discontinuities.
Now, if you put like tangent.
Now, that's a good point. Which trig functions can be undefined? Tangent,
Cotangent.
cotangent,
Secant.
secant,
Oh, cool, that's right.
and cosecant. Because those 4 have what on their graphs? They have asymptotes on their graph, which means you've got discontinuities with those. But if you're dealing with sine or cosine,
You're good.
you're fine because it's just a wave. There's no asymptotes. There's no holes.
It's the fraction.
All right, 43. 43, I have f of x equals x squared, or x over x squared minus x.
A lot of X's.
It is a lot of x's.
I would say there's a hole in this one.
No, there is.
Yeah.
You factor out that X.
You factor out an X.
So factor out an x. Yeah, I want you to factor the denominator. So when I factor the denominator, things become more clear to me.
You one hole and one
So I'm going to say that there are discontinuities at x equals 0 and x equals 1. There is a removable discontinuity at x equals 0. There's a non-removable discontinuity at x equals 1. I have f of x equals x over x squared plus 1. Factor. Can I factor x squared plus 1?
No.
No. So if I can't factor it, what do I want to try to do next? Make it 0. Can I make x squared plus 1 0? No. Why can I not make x squared plus 1 0? Because x squared is always going to give me a what? A positive. And a positive plus 1 is always going to be positive. So that means the denominator can never be 0. So what does that tell me? It is always continuous. There are no discontinuities. Good. All right. So we can tell that there is a discontinuity where? I know there's a discontinuity at 7. I just don't know which one it is. Okay, so I can start off by saying there's a discontinuity at 7. Okay. Now, here's what we want to do anytime we see an absolute value in calculus. Anytime we see an absolute value in calculus, we want to change it into a piecewise function. So I want to change it from this and turn it into a piecewise function. Not difficult. I learned an easy method over the summer on how to change absolute values into piecewise. Step number 1 is take it exactly as it is and rewrite it. Drop the absolute value. So x minus 7 over x minus 7. Step number 2 is change the signs of what's on the inside. So negative x plus 7. If it doesn't have absolute value around it, it stays the same. Now, we need to figure out the domain. And the domain was always the hard part in the past. And I was given a method this year, or this summer, that makes the domain very easy. You always take what's on the inside and set it greater than or equal to 0 on the top. And you take what's on the inside and set it less than 0 in the bottom. And then you just solve each of those for x, and that'll tell you what the domain is. So my domain down here on the bottom ends up being what? X is greater than or equal to 7, and my domain on the bottom is x is less than 7. Now, we should be able to notice that this right here, what happens to this? This right here, it's not 0, it is 1. And this one right here is negative 1. Now, we've already determined that there is a discontinuity at 7. What is it that we haven't determined?
Which one?
Which type? Removable or non-removable?
Close.
All right, now go back to what we talked about at the beginning. How do I tell if something is removable or non-removable?
Cancel out. Is
Before that, what was the definition before that?
If it's a hole.
No, before that. No, quit thinking asymptote. Think of something else. What else? What else did we talk about?
The function value.
No.
Oh, it has to have a
Limit.
oh.
There has to be a limit for it to be removable. If it doesn't have a limit, that means it is non-removable. So what is it I need to think about?
Does it
Does it have
have
a limit?
Does it have a limit?
No.
And if I'm dealing with a piecewise, what do I have to check to see if it has a limit?
Left and right
Left
values.
and right. Thank you. I need the limit from the left. Limit as x approaches 7 from the right. and the limit as x approaches 7 from the left. So, what is it from the right?
Negative.
Which one of these is the right?
1.
The top one is the right, which means my limit is 1. This one is the limit from the left. The limit from the left is -1. Do I have a limit?
No.
Which means my discontinuity is
No.
non-removable. So I have a non-removable discontinuity at x equals 7. Now, what does this thing look like? It says everything greater than or equal to 7, I have a y value of 1, and everything less than or that should be equal to. Everything less than 7, I have a y value of -1. So let's say this is 7. It would be here and over, and here and over. That's what that thing would look like. And now you can tell it's got a jump, and since it jumps, that means it is non-removable. But we figured that out once we figured out there wasn't a limit. All right, one more example. All right, let's look at 65. Okay, I have f of x equals x cubed when x is less than or equal to 2, and ax squared when x is greater than 2. My directions say find the constant a or the constants a and b such that the function is continuous on the entire line. So I need to figure out what a is to make this function continuous. What has to happen for a function to be continuous at a point? I gotta have a limit.
Function.
I gotta have a function value. They have to be the same. So the first thing we want to do is talk about the limits. So I want the limit as x approaches 2 from the right of f of x. I want the limit as x approaches 2 from the left of f of x. What would my limit be from the right?
A.
4a. My limit from the right would be 4a. Everybody understand where I got 4a from?
Yeah.
Because from the right would be bigger than 2, here's bigger than 2, so I need to plug in 2. 2 squared is 4. 4 times a gives me 4a. Limit from the left. Plug in 2, up here gives me 8. What has to happen for this thing to be continuous? The limits have to equal each other. So what do I do with 4a and 8? I set them equal, and that means a has to be 2 for this thing to be continuous. Okay? But don't cheat on me and just go straight into plugging in and then getting the value. You have to understand that you're finding the limit from the right and the limit from the left, and then you're putting those equal to each other. Because there's a problem you're going to work where plugging in doesn't get it done. You have to find the limit, and once you find the limit, then you can get it done. So, don't cheat me. Alright, so real quick, where do discontinuities happen? 3 places. Jumps, asymptotes, holes. Which one of those 3 is removable? A hole. Okay. What makes a discontinuity removable? What did you say? The limit must exist for a discontinuity to be removed.